Ninth lecture of the course on estimation of signals and systems. We have nearly come to the end of our journey. We have studied in this lecture series some estimation problems like signal estimation using input output models, state estimation, system identification, which is actually a system model estimation problem. Today, before we are about to end, this is the pre-final lecture of the series. So, I thought that we have studied a lot of algorithms, some mathematics, equations. I thought we will give you at one shot a flavor of applications and also discuss some of the problems which we have not really treated in depth. So, this is just to give you a flavor of those problems and also to discuss certain industrial applications of these, so that at one go I can kill two birds. So, today we are going to discuss some applications of estimation in industrial instrumentation and control. So, first let us talk about the measurement problem. That is, the basic objective is that we want to measure some quantity for some purpose. One of the very common purposes is to measure a quantity for control. We will discuss such an application later, but you also measure quantities for various kinds of industrial operations. So, today let us first look at what estimation technology can do for measurement. For measurement, we typically, the first thing that is used is called a sensor. Typically it is called a sensor. So, it is a device. So, what does it do? This picture discusses that. So, so here we have some measurement which is a physical process. So, it is a physical process. Maybe we are interested in measuring some temperature, pressure, strain, whatever. There is usually a primary sensing element which is a sensor, which actually due to the, let us say, due to temperature, an expansion of liquid is caused, and this expansion of liquid is the basic principle of the sensing element which we call the thermometer or the liquid in bulb thermometer. Now, usually this effect that the temperature produces is not very easy to measure. We can of course see it as we do in a normal clinical thermometer, but there is often a need for converting this form which is let us say linear expansion into other forms. For example, if you have resistance temperature detectors, then temperature produces a change in resistance which needs to be converted to other forms, like for example that resistance has to be put into a circuit to produce voltage. So, this primary sensing element goes through a series of variable conversions, and after that may go for various signal conditioning and processing units by which the form of the signal is improved. Generally by this time, when it has come here, the signal is generally electrical in nature, voltage, current. So, in the signal conditioning and processing circuit, we improve the signal quality in terms of amplitude, in terms of we filter it, etc. And finally, here we have the measurement which we shall use in our target process. So, this is what we generally understand as a sensor. So, sensing involves a series of variable conversions, and each conversion, remember that each conversion involves a model. For example, the change in the resistance of a nickel sensor due to temperature change is given by the standard equation, that is RT is equal to R0 into 1 plus alpha T, right. So, this is a simple model, or rather alpha T, T is the temperature. So, this is a simple model which relates the T to the resistance at T, this capital T, alright. So, each conversion actually involves a simple model, and each block output, but however remember that these is I mean it is not that simple. So, these block outputs, we may think that this output is actually only dependent on this, but in practice it will be affected by so many other quantities. So, there will be what is known as interfering and modifying inputs, which degrades the quality of the measurement, and a lot of effort is actually spent by engineers to make these blocks insensitive to these disturbance and the interfering and modifying inputs. So, how does, so as we shall see that in this regard estimation can help a lot, right. So, the question is this, in a sense, now that we understand estimation, we know that estimation is basically the computation of one quantity from another quantity using a model, right. So, aren't sensors very rudimentary estimators? So, for example, sensors are simple physical estimators. So, you actually sense the resistance change, and from that you can estimate the temperature, right. So, so in that sense sensors are simple physical estimators. So, if that is so, then we can say that estimators can become very complex virtual sensors if we use complicated models which involve a number of inputs, and if we want to reject noise, disturbance, interfering, modifying inputs, then it acts like a complex sensor. While remember that estimators must compute one quantity from another. So, where will that input quantity come from? So, often the input quantity comes from other sensors. So, estimators often use sensors themselves, they need sensors, and sensors, some complex sense, for example, a typical example is the example of a radar sensor. So, it gets many measurements which are noisy, and inherently it provides, it actually employs estimators within its signal processing schemes, right. So, estimators and sensors are in that sense very close and very similar quantities. And if we consider, so here today we shall see some quick examples of estimators which are used as sensors for measurement and give several benefits, right. So, and real sensing, that is the conventional sensor that we use, have some drawbacks and they cannot answer some questions. For example, what if a measurement cannot be sensed directly? We shall show today that there are some, in some cases you may be interested to measure a quantity which cannot be measured in the situation that the measurement is needed in, right. So, in that case what do you do? Similarly, what if a measurement depends on a number of quantities? So, in that case it is not dependent on only one quantity, right. So, then how to compensate for the loss of a sensor? Suppose this is a typical problem in control, that control requires various sensors. So, if we lose a sensor while we are working, can we make up for it using the other sensors? That's an important question for in some cases. And is it possible to cancel or compensate for the effect of modifying and interfering inputs? We want to improve the quality of our measurement, and we wanted to, since we wanted to infer the desired input, we want the measurement to be unaffected by interfering and modifying inputs. So, the question is, can we do that? We shall see that estimators can answer some of these questions. Okay. So, so we introduce what is something which is known as a virtual sensing, which is basically estimating a quantity So, in that sense, since you are computing its value, it is a kind of measurement. So, but it is not real. So, as usual, I checked up in a dictionary and found that virtual means in effect, but not in appearance. So, while it does not, it may not appear to be a sensor in a conventional sense, it will give you a value for a quantity. So, in effect, it will give you a measurement, right. So, in that sense, estimators can be virtual sensors, and this virtual sensing is actually a technique of measurement that is indirect. So, it is based on other measurements which you make with conventional sensors. It is inferential. So, it I am sorry, this has to go back previous. So, yeah, so it is inferential because it infers or it estimates the quantity. So, it essentially uses an estimation method, and it is often quite improved in the sense that it can cancel the effects of noise, and it can improve the quality of estimation by using intelligent digital signal processing algorithms, many of which we have learnt in our course, and also sometimes by using multi-sensor fusion, that is using more than one physical measurement, we can improve the quality of the measurement. So, we are going to see how that works out. So, I will skip this slide. So, an intelligent virtual sensor is nothing but a device that makes a measurement from a number of, could be possibly a number of conventional sensors, employs an estimation algorithm and improves performance compared to conventional sensing. So, estimation what can it offer? It can offer measurements of inaccessible variables, variables which cannot be measured directly. We will presently see an example. It can compensate for loss of sensors, we will also see an example, and it can give improved measurement accuracy. We have already seen that. We have already seen in the case of Kalman filtering, for example. I mean, Kalman filtering is a burning example where a filter can give you, I mean, vastly improved estimations of estimates of velocity and acceleration from position measurements. So, for example, let me first start with a very simple example. This is an example where I have been involved with this work where we were required to measure. There is a cylindrical ingot which you can see here in this picture. This is an ingot. It's a cylinder. You can see its cross section. It's actually made of steel. Now, the railway wheels are made out of these ingots in the Durgapur steel plant of SAIL. So, they have to cut a certain, the ingot is long, so they generally cut it into three pieces, and they were required to cut it into the right weight, because railways has a requirement that its wheels must be of between this to this wheel, which is a fairly stringent accuracy. In 500 kgs you need to have an accuracy of plus minus 3.5 kgs, which is not so simple to achieve. So, what was required is that they used to, normally people cut it according to some thumb rule that it must be cut at some length, but because of mold dimension variations, this can give quite a bit of weight variation. If the weight is less than 518, then that particular piece has to be rejected. If it is more than 525, then you have to cut out that piece of iron, generally using machining, which takes a lot of machine time and energy. So it uses involves a loss of resource. So what we were asked to do is that can you estimate the cut length for each individual ingot online? That is, while the operator is working, give him an idea as to at what length he should cut using a saw. So what we did is that we actually put two cameras. So the ingot was put on a on a roller platform. So the ingot is on the platform, and you would put one camera on the front. So you get this picture. You get this front face, and then you have one camera on the top. So you get this top view, and then you take pictures. So you get an image. You get two images from this. These are the two images, Now, from these images you have to find out that what is the area firstly, what is the area of this particular ingot, and you also need to find out that what is the that is, you need to find out that at what there is a, this ingot is actually a, there is actually a taper, it is not seen, but actually the ingot cross section is, this is an exaggerated view, there is a 2-3 degree angle taper. So, you need to really estimate this taper angle theta to be able to know that if the area is A here and if the taper is theta, then what should be the, then where you should cut, so that this will give you a particular mass assuming a certain density. So, we did that. So, you see this is here, I can tell you that this is a 2-dimensional signal processing because it is an image, and there are various kinds of estimation involved. For example, you have to have a very accurate estimation of the edge. We must remember that if this in these algorithms, if you make an error of 2-3 pixels, a pixel is one picture cell, then you can have a half a kg to 1 kg variation in the weight of the ingot. So, it has to be very, very accurate. So, all these edge detections, these edges have to be detected for actually getting this angle. Uses very sophisticated 2-dimensional signal estimation using image processing techniques. So, after you can do that, we actually implemented this scheme and could achieve this kind of accuracy. So, you see this is an estimation where we are measuring the volume of the ingot. Now, is the volume of the ingot measurable by any easy way? No, not at all. So, if you really wanted to measure the volume, you can have a detailed mechanical measurement scheme, which is going to take much more time. So, here we had a scheme which is very simple. Just place the ingot on a roller, take 2 pictures, immediately within seconds the estimation algorithm can tell you that what should be the cut length here, such that this volume will be a given volume, right. So, this is our first example. Coming to, let us look at next example. We will skip this slide. So, we are going to see another case study where we want to measure this. This is also a work with which we were involved, and it involves quite detailed estimation, and we had actually implemented it on a machine and have actually tried it in an industry. So, you see what was the problem? The problem was the estimation of tool wear using sensor fusion. Sensor fusion means that you make many measurements and then combine those measurements to compute another quantity. So, you fuse a number of measurements, and generally, as we shall show, that it leads to an improved accuracy, right. So, we will look at this case study of online tool condition monitoring. So, the problem is to estimate the tool wear while the tool is cutting metal without removing the tool, without stopping the machine operation accurately, right. So, for doing that, so this is a picture where you have this is a face milling machine. So, you can so you actually put tools here. So, here you can put a tool, here you can put a tool. This is called a holder, tool holder, and these are the tool bits, and this somewhat looks like this. I mean the cutting edge. So, these are the parts which actually rub against the metal, and therefore, they get worn. You can see that they are getting worn. So, the problem was to find the wear in this is the main cutting edge. So, problem was to find the wear in this main cutting edge. So, typically speaking, you can, if you want to, what is the other way of measuring this wear? The other way of measuring this wear is to take out the tool bit, put it in an optical microscope, and actually measure the wear on the microscope. It can be of the order of 100, 200, 300, 400 microns. Instead of that, doing that, we are interested in estimating the wear while the machine is cutting without removing the machine at all, so that the operator knows that at what time he must replace the tool bits, so that the quality of the surface of the machining and the cutting dimensions remain very accurate, right. So, that was the objective. So, so you see, this was the architecture of the system that we implemented, right. So, we have this is our machine, CNC machine. So, we put a number of sensors here. So, we take voltage, we take vibrations, we take forces Fx, Fy, we take vibrations Vx, Vy, Vz, we take what is that, acoustic emission, sound pressure level, various kinds of measurements we do. So, we actually instrumented the machine with a number of sensors. We take the data, and then as we shall see that we need to process the data. So, here we start processing the data and actually calculate some features from the data, and we try to construct an estimator. In this case, we have used what is known as artificial neural network, which will look at the features and will estimate the tool wear. So, that was the idea, right. So, let us see how that is done. So, these are some of the points where we actually put the physical sensors. So, you have an acoustic sensor here, which senses very high frequency internal vibrations due to cracks, etc., inside the thing. We are not going to talk about that too much. These are the vibration sensors on the spindle, which is rotating, and these are the most important sensors. They give very accurate readings. They are called force sensors, but they are very expensive and they are very difficult to maintain in a typical industrial manufacturing environment. These are another set of vibration sensors. So, we have some current sensors. Current sensing is very simple compared to force sensing. So, as we shall see that we wanted to see whether, rather than using force sensor, whether we can use a current sensor and then estimate the wear, so that we can find a technology which is implementable much cheaper than using a force based technology. So, we go ahead, and so these are some of the signals. You see, these signals are obtained by putting only one tooth in the tool holder. So, therefore, you can see that here this is the period where the tooth is cutting metal, and this is the period when the tooth is idle or not engaged with the metal. So, the forces are immediately coming down to small levels. So, so these are the various sensor signals: force in x direction, y direction, vibration in x, y and z direction, and sound pressure and spindle current, right. So, first thing, look at the kind of signal processing that we are going to do on this. So, you first have this is the original signal. So, it has noise, as we can see. So, first of all, we have removed noise by filtering. So, this is we want to keep the lobes and we want to remove the noise. You can easily make out that they are quite well separated. So, normal fixed filter does the job. So, we got the filtered signals. Next, we notice that these are the parts which are non-cutting, so therefore, these parts do not keep any information. They keep information. The parts which keep information about the status of the tool are the cutting parts. So, we first remove the non-cutting parts, and then we get this what we call the segmented signals. These, it turns out, so now that is a collection of lobes. So, these are the lobes. So, we actually our feature were based on these lobes. So we calculated, for example, you can calculate the area of the lobe, right. So you have to identify the end points and the beginning points of the lobe and then calculate a feature corresponding to a lobe. Then you have one lobe after another coming, and you have to estimate the tool wear in terms of this feature of the lobe, right. So that was the objective. So now once we have these features, we have to set up an estimator, right. So first of all we first of all saw that in this case you must have a multi-input estimator because you want to have multi-sensor fusion. Secondly, your signal model, that is, it is very difficult to establish from mechanical engineering theory what is going to be how the tool wear is actually affected by, or rather how the wear of a tool manifests itself in terms of vibrations in x and y directions, or in terms of forces or currents. No analytical models are available, some heuristic models are available. So we wanted to use a data driven approach where the model itself, we do not have any idea about the so called model structure. Remember that whenever we did estimation, we generally used we actually generally chose a model structure. So we have discussed things like all pole models, pole zero models, all zero models, IIR, FIR, etc. So in this case, since the model structure is known, we need to adopt a structure which can really model, which is very flexible, which can model data from various types. So that was our major motivation for choosing an ANN, because we did not know what it is going to be. Okay, so we chose this data driven approach, and we also found out that in this case the signals are very fast varying, that is, you get signals from sample to sample at maybe 30 kilohertz, but the tool wear is actually a very slow process. So therefore we should not set up a model based on signal sample values, because between the wear between two signal sample values is going to be so low that it will be very difficult to estimate anything. So we thought that we will create the estimator in terms of the feature of a lobe, right. So this was our basic architecture, that is, we took the signals in terms of its features, and then we have to do a signal processing so that we get an estimate of the wear. So as if this becomes a sensor, this becomes a virtual sensor which gives us a measurement of the wear. So we used an artificial neural network which looks like this, and we got some very good results, as we will see. So actually what you have to do now the point is that you have to, in this case you are using an artificial neural network, which means that you have to choose the structure of the network and you have to choose the parameters of the network. So that is a process which is called training. So we did this training. So you create a good number of experimental data, you actually measured the wears using microscope, and then you try to train or optimize your model weights such that the model is able to give you a wear value which is the true value which is established using an optical microscope. So we use typically we use a perceptron, and we use an error back propagation approach for training the perceptron, and we got some fairly good results. So here are some performance results. See that only based on force, if tool wear is estimated using a neural network, these are the estimates, and these are the estimates, and this is the true black one is the true value, On the other hand, if you use force and power as is the case here, you can see that the estimation is perhaps slightly better. Okay. So it shows that if you include another signals, the estimation quantity is likely to improve. Having done our having obtained our results for artificial neural networks, we had also tried estimating the wear based on regressions, and in this case the first thing that we would like to show is that using regression, see, this is a current based estimate. So we use currents and we got this graph. So you can see that it can estimate the actual tool wear fairly well. On the other hand, force based estimates are indeed slightly better than this, but only slightly. These are very comparable estimates with force based estimates. So the first thing is established that using an estimator or a model, you can replace a costly measurement and still get very good quality measurements. Similarly, again the advantage of having sensor fusion in terms of accuracy is shown. So you have current based estimates here, and here you have current and power based estimate. So it turns out that the current and power based estimates are somewhat slightly, not much, but still somewhat improved over the force based estimates or only current based estimates. So that closes this. So you see that we had this is a picture where we had actually taken our setup to actually a factory, and we had done some measurements, and we could estimate the tool wear there. Now we discuss another small case study, which is estimation for control. So what did we see in the last case study? That we wanted to measure tool wear, which is a very inaccessible quantity in the sense that it cannot be measured by, we don't have any technique to measure it while the tool is cutting, but we took some relatively simple algorithms, relatively simple measurements from some sensors, and we set up a model, and we built an estimator which gave a fairly correct value of the tool wear based on those measurements, and online while the machine is cutting, it can predict as to what the present value of tool wear is. So that is what estimation can do to the field of measurement. Now for control, we must, estimators are generally used again in the sense of measurement, because for most control there has to be a feedback. So that feedback is essentially sensing, and we shall see an application of an estimator to ensure that the feedback never stops even if the sensor fails, right. So so this is what I said, the good old feedback control structure. Here you have the reference input, and here is the feedback. This is the feedback through the sensor, and this is the forward path. It turns out that all these elements are actually susceptible to failure. They have they actually get disturbances and noises, so that affects the output. In particular, if there is a failure of, let us say, the sensor, then the feedback loop will be opened simply, and there are certain facts about a controller that we should mention is the following. Remember that what you feedback is actually what you control. So in a control loop, if you add a 1 volt bias to the sensor, then that is, if there is a bias or if there is any kind of noise in the sensor, exactly the same type of noise will actually appear at the output. So the control system is actually traditionally a lot robust with respect to the forward path element characteristic, like even if the actuator bandwidth falls by a little bit or by some amount, even then the loop performance generally will be maintained, but it is extremely sensitive to the feedback path. So if there is anything wrong with the feedback path, immediately the effect of that will appear at the output. This is the property of feedback control. So first thing I said is that what you feedback is actually what you control, and what you can measure, what you can, if you can compute something, then you can reject or compensate it, right? And this is what I said, that the closed loop control is insensitive to variations in plant or actuator, but highly sensitive to variations in the feedback sensor. So now let us consider the following problem. This is the problem of constructing a fault tolerant control system. That is, it is a control system and it will be so intelligent and robust that even if some components in it fail, using the available level of redundancy, that is if another healthy unit is there, etc., it will be able to control the system still and will not lead to system catastrophic failures. Some amount of performance may be lost, but the system will not suddenly collapse. Okay. So that is called fault tolerant control, and so now in fault tolerant control there can be it depends on where the faults are. So the fault can be in sensors, the faults can be in the actuators, or they can be in the controller itself. For this lecture we are not concerned with this controller faults, etc., and I mean, so we will not be considering that. We are mainly in this lecture we shall show that how using, if you have a sensor fault, then, and if you can detect it, we can actually save the operations for many very critical systems. So what happens is that we need to sense a lot of quantities, and we need to always see, the basic problem is to understand whether the system now is behaving like its normal model. So you need to compare things. If it was a normal model and if I receive this input, what is the output that I am likely to receive? I am likely to give out. Am I giving that out? If they are roughly matching, then I am normal. If it is not matching, then I am not normal. So there are lots and lots of sensors have to be used. So a whole thing called an intelligent sensor system must be put in place, which is a combination of some sensors, some of which may be very trivial and easy to put, and electronic processing of signals to obtain better quality measurements. This is an idea which says that if you want to detect whether something is failure, you need redundancy, because you need another copy of the signal with which you are going to compare. So unless you have a redundancy, you cannot compare a signal with something, and you cannot therefore say that whether this signal is behaving quote unquote normally, right. So therefore detection is actually the problem of finding the odd one out, and to find the odd one out it takes at least 2, but even sometimes with 2 we cannot detect which one is the odd one out. So therefore we often need 3, right. And then there are, so this odd one out is the basic principle of detection, which is a kind of estimation problem. So you see, what is the problem? The problem is not a value computation problem like in the previous case. It is a simpler problem in the sense that we only need to classify. So based on the measurement, that whether the system is right now in a faulty state or whether it has suffered a failure or not, right. So for that this detection problem, this kind of redundancy which is needed for detection, can be created in various ways. So for example, you can have a physical redundancy where you actually for every measurement of variable you put 3 sensors. So, you put 3 sensors, they give value A, B, C. So, if A is significantly different from B and C, then A is faulty. So, by the simple strategy we can detect many faults, but the problem is that for everything you are going to put 3 sensors now. So, that is going to cost in terms of money, weight, space, which are very critical in some applications such as aerospace. So, the question is that whether we can generate this redundancy without using a copy, but rather by computation using a model. So, such redundancy creation is called analytical redundancy. So, using these 2 signals, we want to create another signal which we call a residual, such that as long as the system is normal, see the system is normal here. So, this is normal. So, the residual is very small, actually this is actually it will be something like this, it is going to be a very small quantity, and the moment there is a fault, then this residual will rise to a large quantity, so that one can easily understand that there is a fault. So, actually a lot of problems of detection is actually concerned with creating such a signal, right. So, similarly, while you need redundancy for detection, you also need redundancy for tolerance, because tolerance is actually basically tolerance is bring the good one in, detection is get the odd one out, and tolerance is bring the good one in. So, obviously you will have to have a good one, and in many cases it turns out, you see, you can create information from models and computation, but you cannot create energy. So, in many cases if one particular device like an actuator has failed, you cannot really tolerate that fault unless you have some sort of a redundancy available in your system. Now, it turns out that in many cases redundancy is generally available, and all we need to know is how to deploy that redundancy intelligently. So, therefore, we often have redundancy and we need to use it. So, okay. So, let us go directly to an example. So, one of the but sensor faults which we are going to discuss mainly are in a way interesting because of the fact that sensor faults, what is the sensor fault, what is the sensor doing? See, the sensor is actually, I am sorry, right. So, the sensor is actually feeding back signal like this. Now, if it is faulty, if there is any fault here, then suddenly this loop path will be broken, it will be broken and this will become open loop, that will completely destroy the control. So, rather than that, if we have a bank of estimators, these could be Kalman filters, there could be observers, there could be artificial neural networks, there could be various kinds of models which will estimate this quantity. So, it will take the measurements as input, it will also take these various plant signals as inputs. So, it will take these things also, and then it will try to first of all detect whether any sensor is faulty, and then if it is faulty, it will try to compute that signal based on many other measurements. See, we are assuming normally in a process there could be a large number of measurements, it's not that there is only one sensor there. So, the question is that can we construct estimators such that we can calculate the value of a particular sensor without using that sensor, and it turns out that we can, right. So, once we can do that, then we have no problem, because if we can detect that there is a failure and if we can compute the value of this failed sensor, then we need to simply flick our switch from here to here. So, now the feedback path of the control loop is going to be closed like this. So the controller does not understand this difference at all, that whether it is coming through this path or whether it is coming through this path, it gets the feedback. So therefore it can maintain performance. Okay. So now we are going to show an example of that happening, which is for a, this is an aircraft actuator. Now these are very powerful devices, they can create tons of pressure, so, and they are very precise and fast. So therefore they are obviously closed loop devices, otherwise they cannot be controlled. So much power cannot be controlled in open loop. So this is a block diagram of that actuator system, which is electro-hydraulic in the sense that you have, this is a hydraulic servo valve, this is a hydraulic power piston. So using, these are the sensors which sense position. So the servo valve spool position and the piston ram position, they are basically LVDTs. So they give feedback to the controllers, and the controller drives what is known as which is nothing but a coil. So this coil can move this servo valve very minutely. Once, and servo valves have huge amount of gain, so once the servo valve is moved even a little bit, there is a lot of force generated in the hydraulic chamber, right. So you see that this is an actuator, but the actuator itself is a closed loop system, and therefore you have sensors within the actuators, and we are considering the failure of such sensors. So what we do is we first produce an estimation algorithm which gives us this valve position, load pressure and piston velocity. So you see that what you are going to do is you are going to feed these measurements and their past values into an estimator, and then so the whole idea is that suppose you have the pth, the estimator which is supposed to estimate the pth measurement, then you feed all the measurements into the estimator. Only thing is that the general case is yi and I is not equal to p. So accepting yp, you send all of these to the estimator, and then it generates an estimate of yp called y hat p, and then you compare these and using a decision logic to understand whether the pth sensor is actually healthy or not. Okay. So in this case, see, we are showing some cases. In this case, this is the performance of the actuator. So the blue is the command and the red is the response. So clearly the response is following the command. Now if one of the sensors fail, in this case I think what we assumed is that this sensor has failed and we wanted to create this sensor from this is current and this is ram position. So using these two measurements, whether we can estimate this spool position, that is what we tried. This is a simulation which says that if the, so you see that if one of the sensors, in this case it was an LVDT, that is the position of the spool sensor, if it fails, that is if the value becomes 0, then immediately the actuator response becomes unstable. So you can understand that this actuator, if it is part of any aerospace vehicle, then that vehicle may also go unstable. It will create disturbance, it will move away from where it was going and things like that. While if you use the simple fault detection algorithm using an observer, then it turns out that this is this is the performance. So, here the fault occurred. So, there is some initial transient, but then the signal has been estimated and it is fed back, and so therefore, it starts following the pattern again. So, this is actually this actuator was made a part of a full missile model, and then we wanted to see that if such a fault occurs in the actuator, then what happens to the missile. And it turns out that, you see, without the fault tolerant control, the signals that are there, they actually widely differ from what the desired levels of signal should be. So, we will skip these, and so you see that if we have many such estimators, then we need to create multiple such estimators. Note that, for example, say estimator number 1. Estimator number 1 uses measurements 2, 3, 4 and 5. Estimator number 3 uses 1, 2, 4 and 5. So, it uses all the others other than its that particular sensor, and then it compares the estimate with the measurement, and therefrom it gets the various residuals, and therefore, suppose we find that the third residual is large, right, or the fifth residual is large. So, we can easily find out that which is the sensor which is failed. So, this is the way, this is called diagnosis, which is one step ahead of detection, which says that it is not enough to find out which is the that something has failed, but rather than you can also tell which one has failed. So, that is called diagnosis. So, you see that, so we are basically, let's try to reflect, because we are going to end that. So, we see that using estimators we can improve quality of estimates, we can estimate quantities which we cannot measure directly, we can even estimate values where the sensor has failed, and these become very important in certain applications using estimation. And not only that, modern electronic technology, for example, this is a slide on sensor signal processing. All these computations, estimators can be now today integrated with sensors using technologies such as MEMS and VLSI design. So, we can put these estimators on chips and we can make them part of the hardware, and they are not, it is not that you have to put big computers here and there, right. So, that makes this technology very real, and we can have such sensors which can actually communicate. So, using multi-sensor future is now easier. You can actually fuse sensors from different locations, and they can make wireless communications with each other. So, such schemes are going to come, and therefore, use of algorithms is going to explode, and this is the point that I am trying to make, that here is estimation theory which can really contribute to this quality of measurement. So, finally, we have come to the conclusion slide, and which says that there is more to measurement than sensing. So, measurement is not only just physical sensing by a sensor, but using lot of algorithms, much of which is actually estimation. But at the same time, remember that virtual sensing really needs, so virtual sensing really needs real sensing, and so it needs that. And now, so basically we are trying to create intelligence within the devices, which comes from knowledge and which comes from computation. So, knowledge will come from experimentation and learning, that is these are the models which you want to set up. Without the models, no estimation algorithm will work. So, for building the models, you need to do experimentation, and computing can be done today using the technology enablers in hardware and software. So, this is the point that I wanted to make today. Thank you very much.